Okay, so let's get started. So today we are going to talk about some of the assembly code and briefly introduce the lab next week, and which is a 2-week lab for that square problem from Peng Chu's textbook. Remember, we have 2 different textbooks, and one is optional, one is a major textbook, and most of the tutorials are from the first textbook, which we required it. And the second one is optional, and the optional one has a lot of really good examples, and which includes this picoblaze soft core example, and there's assembly code, I think 400 something pages. Let's see. And it has an example in KCP SM3 for assembly code for the problem of doing a addition for a square of the individual numbers, the bytes. And I have a demonstration over here posted to the lab's website. And keep in mind, it's a 2-week lab. Okay, starting from next Tuesday. And after that one, we got a USB. It used to be a tutorial, but I changed it to a lab since we don't have enough time during the lectures to do it. So that's the USB interface with the keyboard. Eventually, we are doing a parity bit check after the 2 weeks lab of the square problem. Okay, so that's the plan for the rest, and then we'll add 2 course projects, 2 lab sessions for the course project. And so the main idea for now, if you have better ideas, just let me know. But I know you guys are super busy with a lot of things, which prevents you from being creative. That's what I really know. Sometimes you don't have time to think, right? I just realized this when I was teaching at Mines. Students are taking like 20 plus credits over there. So they hate it. They just don't want to do anything extra. Just want to get the thing submitted. But I think here's better. I give you guys a room for the project. So we hopefully during these 2 live sessions we're not doing new things. However, I'll give you some tutorials to follow, and eventually I'll let you guys create something. Okay. So one of the problems for FPGAs for here is it can become complicated really quickly, and doesn't like microcontrollers, right? It has a CPU in there. We can directly program with a higher level programming language. This one has to start from assembly, and there's no C compiler for this course. So eventually, everything has to be controlled in assembly, and we don't have libraries available like Arduinos. There are libraries everywhere. You just load that the header file of the LCD and eventually throw numbers to the LCD, all the APIs, the functions, and eventually can display something over there. So for here, it takes one entire lab session to display something on the LCD. Okay, so how can we still contribute to not this field, but some sort of like new ideas instead of like other people are judging, saying, hey, there's already a sensor available on the market, you can just directly purchase and use it. Why not doing that? Okay, so I think we can customize a lot of things by designing a sensor. You know what I mean? So there are a lot of sensors available on the market. If you're trying to use IPGA, I'm trying to beat the i7 core, it's impossible, right? So, however, if you are designing a specific sensor for a specific application, then that's going to be something that doesn't exist on the market, and it can contribute to a certain field. For example, for light sensor, right? For light sensor, and you are trying to convert analog signal of a certain light and digitize it and send it to the CPU to do something, okay, for certain communication. And that will be a really unique design. So that one involves ADC. Eventually there will be an ADC module available for the IPGA. So that ADC project was a course project from last semester. It's available online. You can directly use it and eventually digitize an analog signal through the ADC. And eventually that digital signal can be sent internally into the FPGA to your digital blocks and eventually communicates with other peripherals through digital communication ports, for example, SPL or UART. So you probably have used some of the digital sensors in the past. For example, the light sensor, right? So you can purchase a light sensor like this one. Let me just show you. This one. Okay, this little module. So someone sells this one, is making a lot of money. All right? And this is application-specific sensor. It has a digital port, which is a standard SPI port. We're going to learn it in the next few weeks. Okay, so you'll know how to design a SPI port block in the IPGA. So this is very simple. It's input outputs, right? So inputs taking certain clocks to get all the digital data in, and then send it out to the other peripherals in the IPGA. So, however, the sensor itself is over here. Definitely, this one has the ADC in it. Analog to digital converter. Okay, so this one is a photo sensor. You can imagine it will be a photodiode, not photodiode. It's a yes, it's a photodiode, right? Photodiode receive photons and convert the photons into photocurrent, and that photocurrent goes through a certain. Let me draw it for you really quick. You should be familiar with this circuit. This is basically everywhere. Should go here, yes. And then again, do this. That's a gain resistor. Let's call it RF, okay? So this circuit is probably familiar to you guys. It's different from this one we learned in circuits, okay? This is if this is providing a V in here. I mean, everyone graduated from this program should know this clearly, okay? So what is this called?
It's an op-amp.
Yeah, but what kind of op-amp? What kind of configuration?
It's inverting.
Inverting. Is this amplifying current or voltage? Is amplifying current or voltage?
Voltage?
Yeah, you can say voltage. However, this is also called TIA. So remember when someone in circuit 1, whoever taught it, was deriving the voltage gain for this circuit, what they do, or what they did. The 0 volts, because of feedback and infinite open loop gains, eventually this is 0 volts as well, right? So how did they derive the voltage gain? It's V in minus 0 volts over R1, because current is not getting into it, has a super large input impedance, so eventually current goes this way, right? Okay, so V in minus 0, the KCL, so the current is not going inside, so all the current getting in into the joint here will exit. So eventually current in equals current out. So this is current in, and current out is 0 minus V out over RF. And this gives you V out over V in, which is minus RF over R1, right? Okay. So when you are deriving this voltage gain, you are using current. So did you notice that this is actually a current to voltage converter? Okay, very fundamental and basic point over here. But during the interview, you want to let whoever interview you know that, okay? If they ask you is amplifying voltage or current, you should say, hey, this is actually amplifying a current. Okay? And this is called TIA. This amplifier, yes, you can say it's the inverting configuration of op-amp, but also this is fundamentally it's a TIA, it's transimpedance amplifier. Transimpedance means it's converting current to voltage. It's basically flowing a current here and then amplify and change the current to the voltage output. And then you can look at this configuration. It's very similar to this one. I just removed the input resistance over here. You can definitely add a resistor over here without any problems. However, this is another example for the TIA. We usually use this one for a pixel. So if you think about the pixels, the cameras in your phone or everywhere, any digital pixels. This is a little pixel. It's a photodiode. If you are in digital VLSI, you can lay out a little diode. Okay. So in silicon, if you lay out the diode and reverse bias it, and eventually whenever it receives, it just needs to be a regular diode. It's really amazing. It's amazing. So if you reverse bias a diode, it's just simply a pin junction. And so in that case, you have your little silicon die in your circuits. Excuse me. And definitely you want to open up the cover, so expose the chip, the metal strip, the top metal, whatever. So this one should be exposed, and the chip is able to receive light through the silicon dioxide, which is transparent. This is really thin. Okay, so it receives that signal. It's a pin junction, and there will be a very tiny photocurrent going through the diode in this way. It's really weird, right? So usually you are thinking, hey, it has to be forward biased in order to run something through it. So if you are trying to do this, okay, forward bias it, this is called LED. It's a light emitting diode if you forward bias it. If you reverse bias it and connect to a TIA, this is not an LED anymore. It's doing something reversely. And this is called a photodiode. Instead of emitting light, it absorbs photons and converts it to photocurrent. Okay, really interesting, really useful technology. So if you do this, connect to a TIA, so and place this little thing in a little pixel and have, for example, 100 by 100 pixels, and it forms a camera. Okay, it forms a camera. So what's happening over here is receive a light, and because this circuit, remember, is just one loop over here, it's not getting into the op-amp. So eventually, the photocurrent goes through the gain resistor over here, and eventually flows to ground. It eventually forms a voltage drop for VL. So depending on the amount of photons being received by the photodiode, you are getting a different photocurrent, a varying photocurrent. And that photocurrent times that gain resistor will give you a different or varying voltage drop at VL. So a stronger light will give you a larger photocurrent, which results in a larger voltage drop or a larger voltage. And then you connect this one to an ADC, right? Analog to digital converter, and that voltage will result in a larger digital voltage. Okay, so you got a digital like 8-bit, for example, 8-bit digital output, and you can send that one to an ISPI port, and use the interface with Arduino, right, to do something. So this is a basic light sensor structure from scratch, from light to Arduino. Okay, this is one example for light sensor. If you come back to this example here, this guy. So everything from this paper everything here, including the photo sensor, everything here has been highly designed as a VLSI or integrated circuit chip inside this sensor. Okay, so this sensor has an ADC in it, has a photodiode in it, and eventually just directly send out ISPI digital lines. That goes with SCK, SDO, all these kind of digital lines. So someone designed this sensor, is making a lot of money. They can sell the sensor as a digital sensor, right? That's one of the examples. So for our project, the goal is to design a digital sensor. It's one of the ideas. You can find any analog signal. It could be a temperature, could be light, could be a resistance, potentiometer, resistance output for some reason, okay? And since IPGA has ADC, so eventually we will use that ADC as a ADC module. We may need a TIA or an amplifier to pre-amplify the analog signal, and that's a very important skill to learn, I think, for you guys. So I was looking at someone doing senior sum for a group. I didn't even know how to pre-amplify analog signal first. So I do have examples when I taught analog in one of the labs. This is a really practical problem. So just imagine that there's an analog signal from a sensor. How to deal with it? It's a really practical problem, right? We have analog signal everywhere. It can be audio, can be light, can be temperature, can be anything. So how to deal with, how to eventually digitize it and convert everything to like 8 bits or 10 bits reliably, so you can load it to the CPU for computation, for display, for communication, for all these kind of things. But however, you have to reliably convert it to that 8-bit or 10-bit digital data first. How to do that? Okay, so I have one example here. We did a oximeter a few years ago in analog labs. So you know how the oximeter works. It's detecting your pulses at the fingertip, a little clip in the hospital, and eventually can detect your heart rate. So the way that works is emitting a IR light, and since your blood, the red blood cells is able to absorb oxygen, so whenever your heart pushes the blood to the fingertip, so the blood vessels has more blood or red blood cells in it. Okay, so when you have a IR light emitting to the fingertip, because there are more red blood cells, and so eventually it shows that there are more oxygen in it, because there are more red blood cells, and red blood cells absorb oxygen from your lungs. Okay, and then red blood cells absorb these IR lights, eventually leaves less IR light reflected to the sensor. So there is one emitter, one sensor. So this is emitter, IR, infrared light emitter. Another one is a sensor. Okay, if the red blood cells, if you have more red blood cells which absorbs more light, there will be less reflection. Okay, for the sensor. And whenever your heart pulls blood back from the fingertip, okay, eventually there will be more reflected IR light, because less emitted IR light are getting absorbed by the blood. So eventually, because you have a different amount of red blood cells at the fingertip, during different time frames, so you are seeing a different received reflected IR light by the sensor. Okay, and then you can use a peak detection circuit to find out. You can see this, right? So depending on the amount of red blood cells in the fingertip, the receiver is receiving a different intensity of the light, which is converted to the electric signals. So eventually you can display everything in the oscilloscope, and then you can use your cursor to measure the time difference between these 2 points. Just do a peak detection, right? And you can measure the time difference between the 2 peaks, and eventually convert it to heart rate. Okay, and so first you have to be able to convert that analog signal from the fingertip to a digital signal first. So in that case, you need a few different stages of filters and amplifiers. So we'll talk about this later, not for now, but later. And this could be a really typical problem you will see in the real world, because it's a random analog signal, it has a random DC offset you need to remove. Keep in mind, this is super, super important point as an electrical engineer when you are trying to design something, okay? So in the senior SEM, I saw people don't even know like there's random DC offset directly shorting that analog signal into the ADC and trying to make it work. That definitely it will not, because all these analog sensors is giving you some random DC offset. If you look at this one, okay, so this is a 0 base point. Eventually, it's being lifted by some random DC offset. Okay, so for any analog signal from the sensors, you need to do some signal processing first using circuits. Okay, it could be a high pass filter to remove the DC offset first, and then low pass filter to remove the noise, and eventually amplify it at a certain level. So, and also should know, depending on the amplitude of the analog signal, you want to choose appropriate voltage gains for each stage. Even though you need 100 times the gain, but you cannot do it 100 times just by one stage, because it's also amplifying the noise a lot. You need to amplify it for example, 5 times, okay, first, and then remove the noise, and then do another 5 times, and then do it another 5 times. So it's going to be 5 times 5 times 5. Will be eventually 125 times to reach the goal, instead of doing 100 times once, because it's also amplifying noise. You need to do it one time and filter out the noise and do another time, you know. So all these design considerations you need to know as an electrical engineer in the future. Okay, so we will. I'm going to give you some options for the analog sensors for you guys to use, and I'll give you the circuit to use to start with. And you can modify the resistor and capacitor sensors to change the cutoff frequency for the filters, and eventually receive or output a reliable analog voltage, which is detectable by the ADC you have for the IPGA. All right, and the IPGA will receive that and convert it to a digital signal, and through the SPI port, export it to something. Okay, eventually, even though everything is still in the IPGA, but you can imagine if you really want to customize it into a digital sensor in the future, you can basically, if you have the money, have the funding as a startup company, you can definitely tape it out through TSMC and sell it. Like these guys who are selling these light sensors. Okay, so these light sensors are like $8 to $10 for each, including the PCB module. Okay, so this is some of the ideas I have in my mind for the course project. Okay, we do have a lot of time to work on that. It'll be a lot of fun. Okay. I may want to remove this one. I don't know. I'll make it easier. So I'll let you guys go through the necessary ones as soon as possible. So at least we will be able to either use UART or SPI. So we are not expecting I2C. The I2C is really easy to use, but all the Verilog code behind the scenes is very complicated, like 5 pages or so of Verilog. So I think it's okay to use UART, just RxTX and SPI. It's easier protocols, but not as reliable as I2C. Do you know any sensors are using UART? It could be interview questions, and then to check if you're a real engineer or fake engineer. You told me you told whoever interviewed you, I have used a lot of sensors, this sensor, that sensors, But if they ask you could you give me an example of a digital sensor that use UART as a digital port? It's really interesting in the industry. A lot of companies are using the same digital port for a certain type of sensor for some reason. Probably because of for example, UART. Okay, UART. It's usually 9600 baud rate, right? It's really slow, and it's very reliable. And a lot of times UART is being used for wireless communications. So any wireless modules like Wi-Fi or Bluetooth, okay, you can find out they have RX and TX on it. It's probably because it's very slow. So it's not probably a little bit resilient to high frequency RF signals. Maybe, I don't know. And for SPI, for SPI, usually can find SPI on SD cards. Okay, why is that? You can think about, so what are the requirements for SD card communication? Let me ask you a question. So in the past, the SD cards are usually like a 250 megabytes. I mean, one was little. But now it's usually like a 32 giga, at least.
They're huge.
Yeah, they are huge.
Yeah.
Who is taking microcontroller in the fall this year? Okay, a few. So we'll do some SPI reading and writing to the SD card. So the SPI, because it's huge, sometimes can be like 32 gigabytes. So if you are reading and writing to the SD card, it takes a lot of time. If you are using UART, it's gonna take 10 years to read and write the SD card. Okay, so you need that port to be what? To be fast. And SPI is fast. Okay, I2C is slow, a lot slower than SPI. So that is why we don't want to use I2C for SD card. Okay, so SPI is usually used for SD card. And what about I2C though? I mean, what's the benefit of I2C compared to SPI?
They have a lot of sensors.
You got a lot of sensors, right? Yeah, have addresses and all the sensors. What else? How many ports for I2C? How many ports? 2, right? SDN, SCL. Right? Just clock and data, 2 ports. So saving a lot of pin resource of the microcontrollers. For SPI, how many? 4. All right. So that's another benefit of using I2C. All right. So I2C is slow. So in that case, for example, for the application we did for the Pokusa Springs hot tub temperature sensor, and there's no power supply for each hot tub. They want to keep that natural scene of the resort. So that's why they want to drill holes and have all the construction to be done to the hot tubs. So in that case, sometimes it could be we need a real long cable for data communication. So for example, we have to sense the temperature of the hot tub and send it wirelessly to the whatever server we build. Okay. So in that case, I can give you multiple options. You probably have learned thermocouples in M&I, I guess. Did you? Yeah. Thermocouples. So thermocouples is like a resistance or voltage based temperature sensor, right? So depending on the voltage, you got a different temperature. So do you want to use thermocouples for this application or not? Why not? Why or why not?
You wouldn't because of the long series resistance.
Mm-hmm. Yeah. So do you want an analog temperature data to be sent through the cable, or digital signal be sent through the cable? Digital, why? It's more resistant to what? To noise. Yeah. So for analog, it's reading every single step of the analog voltage, right? So for example, the sine wave. Is there a little noise? Then it's going to change from like 1 volt to 1.1 volt. And you have a long cable. It's sometimes you got a little surges somewhere, and eventually the voltage, which carries the information of the temperature, will changes along the line, along the transmission line. Okay. But digital is fine because digital only reads 0 and 1s. So if there's a little noise in there, it's just changing 0 from 0 to 0.1, but it's still reading as a 0. So it's more resistant to noises. So in that case, when you are sensing the temperature, thinking about the hot tub background, you want to digitize your analog temperature data right in the pool. Okay? So whenever the analog temperature is getting sensed, you want to immediately digitize it into the digital signal and store it in the memory. So in that case, you want to use digital sensors. And digital sensor is going to send the digital data by clock through a long transmission line. And in that case, for example, it's like 50 meters. I don't know if you guys are familiar with meters, but
Yeah.
America. Okay, so 50 meters, for example. Okay, 50 meters. I tested, so I used the Cat3 line of the Ethernet cable. I can do over 100 meters without any problems. However, I shouldn't use SPI. Why is that?
Probably because I mean it's faster, but it's still sending like I guess like because the way it works.
Yeah, if it's too fast.
Yeah.
If it's too fast with a long cable, the cable has parasitic capacitance. It's capacitors everywhere, even though you don't see it, but actually it's everywhere with the cable, with the rubber material, metal to metal. The rubber is a dielectric material, so it's forming caps along the line. So eventually, if you're running the signal really fast, it won't be able to charge and discharge efficiently to the little parasitic capacitance. Okay, so high speed won't be able to transmit through a long distance. So in that case, you need a slower communication ports. So it could be I2C. So I2C is actually able to transmit digital signal with, I think, 40 kHz through 100 meters of Ethernet lines without any problems, which is amazing. So in that case, you want to choose I2C instead of SPI. Okay. So these are all the considerations for selection of ports for digital design. So when you are thinking about your course project, find out a sensor that can be used to improve human life in your community. Can be anywhere. Back to your country, back to anywhere, your hometown, and think about any applications. Could be in your house, could be in anywhere. That a little sensor converts analog signal from the environment to a digital signal, and everything will be implemented or embedded into your IPGA. Because your IPGA has ADC in it. Okay, so it's going to be a digital sensor you can use to make money. Okay. All right, we'll give you some examples. I'm going to give you some examples for the digital sensor you can use for a project. But now just I'll let you guys know this earlier so you can start brainstorming on it. All right. Any questions on this by far? Okay. So eventually it will be a digital sensor similar to this light sensor. Similar to this light sensor. Okay. This one. And do some research on it. There will be a short introduction section with the literature study. Okay, why you want to design this sensor. So for example, ADC has, analog device, that company. Okay, so AD, that company, has this sensor, but it doesn't have this port for this application. So here, why I'm designing this sensor to solve this problem, to fill this gap. We can actually publish it, right? You can verify the sensor through several experiments. Eventually, we got a paper, can submit it to IEEE conference as a 4-page paper, and I can send you to their to present. Very possible. So in that case, you need the time to work on it, right? So that's why I'm giving you 2 weeks over here and 2 weeks over here. Okay. But they're doing the same 2 weeks. So not 4 weeks. Anyway, still have a lot of time. I think the end of semester. So we don't have a final exam. You know that? Do you prefer a project or final exam? Which one? Project. Yeah. So eventually, it's gonna be a final project presentation. Here, I think, right? So it's 1, 2, 3, almost 3 weeks. 3 weeks to work on it. All right. Probably we can have a lab session to let you build that preamplification circuit. So everyone can learn how to do it. I think probably you didn't learn that from other classes, so it could be a very important skill to learn. All right, let's come back to this soft core stuff. too much something. Careful. Okay, so question number 1. Toggle bit 5 of a register S0 which holds a byte in there because this is an 8-bit core, and send the result to S0. So open up the web page, which is, if you refresh the browser, you should be able to see a link here. March 6, there's a link. If you couldn't see the link, just delete the cookies of the browser and refresh it one more time. You should be able to see that after you refresh it. Open it up. There are a couple of examples from Peng Chu's textbook. So this is about the masks. All right. So what is a mask? A mask is something you can do an AND, XOR, or OR logic with the existing byte. Try to manipulate some of the bits. Okay? It's called a mask. So the mask is usually constant. So, see here. In assembly, you can use a constant to rename the mask as, give it a different name, so to make it more meaningful. Right? So for this one, you can see it's called the set mask. The set mask. So for the set mask, it's basically a byte, but has a 1 at bit 1. Right? And when bit 1 is doing OR logic with S0, it's setting bit 1 of S0, but all the rest of the bits are not changed because 0 or something is still that thing, right? But 1 or something will set it. And remember, this instruction is directly, so my question for you guys is it changing S0 or not?
No.
Is this just to temporarily store the result somewhere, or is basically sending it back to S0? It's modifying S0 directly.
Actually, yeah, that is modifying.
It is, right? For C, it's not. For C language, when you program it in the past, it's not. But for this one, it is, right? For assembly, it is touching the very bottom. So actually, after this operation, S0 is changed, is updated. So if you're reading the question from the in-class answers from the paper, right? So it's asking you to send the result to S0. Do you need to send it one more time to S0 or no? No, it's already updating S0. So you just need one line, right? If it's asking you to toggle that bit, you just need to do an XOR operation, and you know if you are using a number to XOR with 1, it's toggling that bit. If it XOR with 0, it's not changing that bit, right? So for question number 1, it should be XOR operation with a certain mask, targeting that bit 5, and eventually it will update S0 itself. You got that? Is everyone finishing the first one? Okay? And the second one, clear bit 1. Clear bit 1. And now it's changing the register. It clears bit 1 and send the result to S0. So to clear the bit 1 of S1 and send it to S0. How to clear it? Do an AND operation, and with that certain bit to be 0, right, in the mask. But all the rest should be 1s. It's like this one. Clear mask like this one, okay? So if you are clearing that bit, you put a 0 there, but all the rest should be 1s. And then do an AND logic here. So it's going to clear that bit. And eventually, that S0 will be updated. If you want to send it to a different register, which instruction you want to use? I want to send the data in S1 to S0. Which instruction should I use? Load. Can you directly load a register to another register? You're seeing examples. Oh, I can load a number into a register, but can I load a register to a register?
I don't see why not.
You don't see why not? Yes. So you can just go to where's the reference? Here, right? So it's either in Pengchu's textbook or it's in this tutorial, soft core tutorial, where you can find that load instruction. Okay? Are you allowed to load register to register? Yes. So you can do both. Load a register to a register or load a constant to a register. Okay? Is that clear on the second question? Any question on the second question? I move forward. Yeah. Okay. The third one. Set and load. Very simple, right? Okay. Any question on number 3? No? We don't have one. Any question on number 4? What is number 4? Use assembly code to check bit 7 of S0. If the result is 1, assign this to S1. Otherwise, go to address symbol done and do nothing there. Which instruction you should use? Check a bit. Check a certain bit.
Yes, be test with that mask.
It's over here. See this one?
Yep.
So what is test doing for you guys? Take a look. What is test doing? Here. Okay, all these are very good examples, could be on the quizzes. Since we don't have final exam. Don't have too many things to scare you guys. Quizzes.
Well, test is just directly comparing the two. It's ANDing them.
Yeah, it's doing a bitwise AND logic, right?
Yeah.
Okay, and eventually if the result is 0, then flag Z will be 1. Okay, so one question. So is the flag Z the universal flag or just for this operation? Is it shared by everything else?
It's a show.
It is a universal one, right? It's a shared. Okay. So it's just there's just one Z flag, just one. Okay. Let's come back here. Keep in mind it's a bitwise and logic. Okay. So it's asking to test a certain bit. So you want to create a mask first. So for this one, I'm creating a mask has the MSB to be 1. So the A0, it's a hex number, so it's going to be 1, 0, 0, 0, and 4 zeros. Okay, so it's a bitwise AND logic, so which means this guy is doing a bitwise AND with S0, Okay? Because all the other ones are zeros, so it's going to clear all the rest bits of the S0. So if the result is 0, it means what?
The Z flag is 1. If the result is 0, the Z flag is 1.
Yeah, it means the MSB with S0 is 0, right?
Yeah.
Is that clear? Because this is 1, right? If S0's MSB is 0, it do an AND logic with this guy, and the result will be all zeros. so the Z flag becomes 1, right? So which means if non-Z, which means the Z flag is not on, so don't worry about that for now. But if just in case if the Z flag is on, done. Okay, do nothing. Just done. Colon nothing. All right. If it's non-zero, which means S0 is not 0, or MSB of S0 is not 0, come here to do something, right? And eventually, so after it jumps, so it skips this guy and jumps here, and what's next? In the instruction memory, what's gonna happen for this code? What's the sequence? Just doing this check, right? Non-zero, which means so it's not non-zero. It's it's non-zero. So when 0 flag is not on, right? It jumps to MSB set, jumps to here, this address. Okay, it jumps to this address and do this, whatever you're putting here. What's next? Is it going to come back to this point, or is it gonna move forward?
It'll just move forward.
It's gonna move forward. Okay, we'll still move forward to down and stuck there, right? If Z flag is on, it's gonna skip this non-zero line and go to jump down and directly skip this MSB set and directly go to done. That's how that works, okay? Give you guys like 1 minute, 2 minutes to finish, to think about question number 4. Checking bit 7. Checking bit 7, okay? So what is that hex number? Still the same number. Okay? I just made it so easy for you guys. So the first line is not changing anything, right? It's the first line, just copy the first line, okay? What about the second line? You can use jump Z. Let's use jump Z. What about jump Z? Not non-Z. Let's do a jump Z, okay? Start writing jump Z, comma. Do something. So jump to Z. So if, because the question is asking like if the result is 0, okay? So so which means whenever it jump Z, so whenever Z is 1, it jump to another address. You can name whatever the address you want to name it. Okay? And in that address or at that address, you do a load. Okay, you load S0 to S1, right? Okay? So in that case, if it's not 0, which means it's gonna skip that jump Z and do the next line and directly jump to done. It's very similar to this guy. So you wanna add a jump done like this and put a done here as well. Is that clear? Any question on this? No? Okay, we'll do another problem and I'm gonna give you 5 minutes to take a break, okay? So let's move to number 5. Any question on number 4? One more time. It's okay to ask, okay? What's that?
Can you explain that again?
Yes. So number 4, when we are looking at this one, okay, it's a very similar problem. So this one is doing a bitwise and logic with these two numbers. So if S0's MSB, let me write it down here. I'm pretty sure other people probably also have this question. Okay, so S0, 0, 1, 1, 1, 1, 1, 0, 0, like this. Okay, so if S0 is this, and your A0 is this, okay? This is 0x A0, okay? So this is the mask. And S0 is this guy. I'm doing a test. I'm doing a test. So tell me what is Z will be.
Z would be, wait, S0 is, if F0 is 0, then it would be 0.
Mhm.
Otherwise it would be 1.
So Z is what?
Z is, what is this?
Z is 1, right? So Z is on. Why is Z on? Because the result for a bitwise AND logic for all these bits eventually gives you 0, 0. Okay? So basically this, I'm setting the masks MSB to be 1. So I'm testing actually the MSB with S0. Because if this is 0, it's giving a 0. If this guy is 1, for example, if S0's MSB is 1, what's going to happen? Z equals what?
0.
0, because 0 flag is not on, so 0 is, Z becomes 0, right? Okay, so in that case, if the MSB of S0 is 0, so eventually you are getting a 0, so Z becomes 1 because 0 flag is on. If 0 flag is on, which one should be executed in this case?
Just go jump to down.
Here. No. If 0 flag is on. If Z is set or 0 flag is on,
Okay.
where it goes. Oh yes, that's right, yeah. 0 flag is on is going to done, right?
Yeah, okay.
If it's non-Z, it goes to MSB set. All right. It's recorded, can always come back to this video to check, right? So similar thing for your problem number 4. Similar to problem number 4. Okay. So number 5. Extract bit 5 of S0 and load it to S2. Where is bit 5?
Yeah.
So these are the byte, right?
Yeah.
This is bit 0, bit 1, bit 2, bit 3, bit 4, bit 5. I'm trying to test or extract bit 5 of S0 and load it to S2. What should you do? Let's still use test. Okay, let's still use test.
I guess we.
So eventually S2 is holding what? So load it to S2. So S2 is holding what? Holding a 1 bit, right?
Yeah.
Holding a 1 bit. So that result could be only 1 or 0. So eventually S2, how many bits are in S2? How many bits are in there?
It's 8 bits.
8 bits. So eventually it's just LSB, right? Just LSB. Because 8 bits holding a 1 battery number is basically just holding that number at the LSB. Either 1 or 0, okay? But all the rest are all zeros. Okay? In that case, you do a test. So if bit 5, so which mask you should use? Which mask?
That should be 2, 0.
Mm-hmm.
Yeah, that's the hex number for it.
So look at this one, because this mask is trying to test the MSB. So it's 1, so the A0, right?
Yeah.
If I want to test this one, so I want to give a 1 here, but all the rest are zeros, right? So eventually this is 2, 0, right? So it's going to be 2, 0 as a mask. Okay, 2, 0 as a mask. So if 2, 0 is the mask, so I want to do a test. You do a test, this, replace this line with it's test, is that S0? Yeah, S0, comma, 2, 0, okay? What else?
So I guess
If it's 0, then what? Eventually the result is 0, Z becomes 1, right? If Z is 1, do what?
you just finish. Because I guess there's no need to change it. Right, because if they're. It's
So I'm testing that bit, okay? And I test it, it becomes 0. So I know, it's a 0 there, it's a 0 there. Even though I'm trying to extract it, but am I really extracting it? No, I'm faking it, right? So eventually I know what that is, I'm just fake it, I just put a number into the register. There's no way that I can extract it. It's just, but 0 is 0, right? It's like $1 is $1, doesn't matter who gave to you. Okay, so it got a 0 there, it's just give a 0 to that register. Do you care about the $1 who gave to you? No, just take it, right?
Can you not put logic inside like the other part? Like I know in AVR you could have done like load S2, S0 and with the mask and then you could like extract it like all on one line. Do you do that without doing like the test thing here?
What's the instruction being used for AVR?
Just load.
But how to load it? Just load, it's transferring, right? But how do you extract it?
The assembler would kind of put it together with, because if you did the original register and you anded it with the mask, it would extract it and then you load it back into it.
But it's so now it's a different register, right? Because now it's a different register, so I have to load it one more time. You have to load it externally. So how to extract the AVR? And did you say and it? Just and it? Yeah, and it will give you the result. That bitwise and, right? It's just a byte, a result in byte, right? Then it could be either. But the thing is, if it's not 0, then that 1 will stay at that bit, right?
Yeah.
I think what I mean over here is a very good question, because what I mean over here, it could be a little bit confusing. That's I know why you're asking, because I extract that bit. I'm trying to show the bit as a 1 or 0 instead of the bit as that location. You know what I mean? So bit 5 over here is 32, right? It's a 32. So I'm trying to detect it's a 1 or 0, not a 32 or 0. You know what I mean? So eventually you extract that bit, it's just a 1. It's like a 1, not a 32. And then I put it back to another register as LSB. But that's a very good point. Okay? So basically I'm taking it out. It's either a 1 or 0, and then I put it to the LSB of the new register, which is S2. So if it is 0, I shouldn't do anything, because the original S2, I assume it was 0, all zeros. So just don't do anything. Just go to done, colon, nothing. Okay? And next to that jump, next to that jump, which means it's not 0, which means it's a 1, then you do something to S2. And what is that thing? That's the $1 thing, right?
Yeah, you just load 1, because if it's non-zero, you just add 1 to the,
Not add.
Well,
because
not add, but you
add,
can
load.
load it.
Yeah. Alright, I'll give you guys a few minutes to think about this, and let's take a 5 minutes break. Let's rest.
Sorry, I don't know if I was speaking well, but I was more thinking like, couldn't you just do this where you like check it? And then you bit shift it over, and then you're just setting the 1 in load.
I don't think picoblaze has this thing
Oh,
can be
okay.
compiled.
Okay,
No.
cool. Yeah, I think I was thinking AVR.
Yeah, AVR compiler is more powerful
Or
than
like
that.
x86 or something.
Yeah. All right, let's keep moving forward and finish up this one so I can go home and pet my new dog. Miss him so much.
When are you gonna bring him again?
I can bring him over today after lunch. He's coughing a little bit.
Him and Bailey could be friends together.
I think so too. Yeah, yeah.
They'll always be.
He's super mellow. He's super mellow and chill. Only 11 months old, but really chill. Okay, we are at problem number what? 6. So 6. A 16-bit binary number is stored in S0 register and S1. So because all these registers are 8 bits. So sometimes you need a 16-bit binary number. So which means one of the byte should be an upper byte and another byte should be a lower byte, right? And you do a concatenation eventually to form that 16-bit binary number. Yeah, so just treat them differently, right? So when you are dealing with all the bytes, eventually when they are in the registers, there's no difference. These are just the binary numbers. However, if you treat them differently, and eventually you can use one of the register as the upper byte, another one as the lower byte, okay, for the computation. And it's asking you to use assembly instructions to shift the 16-bit number to the right by 1 bit. So which means the LSB of S0 has to go to the MSB of S1. Do you agree with that? Do you agree with that?
Yeah.
Yeah. How do you do that? Test.
Yeah.
I test the LSB of S0. If it's a 1, I put it into the MSB of S1, right? Yeah, but there's a better way to do it. See, if you look at the instruction here, these ones. See which one you can use. Which one can use?
SRS.
Which one is the good instruction to use?
SRA, it's like shifting the whole thing, right? I would
So should be shifted to the right. Okay, so should be something on the right hand side, right? What about SR0?
No, because you're just
So it's shifting. It's adding a 1 to the left, which makes sense. You're shifting everything. The 16-bit to the right is adding 0 to the front, right?
yeah.
Okay. However, it's shifting the LSB to C. What is C? The carry bit. Okay.
Yeah.
Okay. Then what else? Take a look at the instruction explanation here. Oh, should be SRA or SR0.
So, SRA, right?
SR0 doesn't do anything else. If you look at SR0, do I have an example here? I don't. Let's look at this one. See if I have an example somewhere. SR0. Oh, I don't have example.
Yeah.
Anyway, so but at least we can tell it's not doing anything else, right? It's just shifting everything to the right and LSB to C and 0 to MSB. But still in C. Okay? Then if you do a SRA, what's gonna happen?
It's gonna take the last bit.
C goes to MSB. Could you combine or maybe just use one of them or combine them, whatever? What do you think? How do you shift the entire 16-bit to the right? It's basically still they are still stored in the two registers, right? It's just S5 or is that S5? Yeah, S0, right? So S0 becomes the upper byte, and S1 is the lower byte. It's not changing. They are still holding these two bytes. The only thing is the numbers in there should be changed by shifting. So which one should you use? If you do SRA, okay, to the upper byte first, what's gonna happen? So the LSB goes to C.
Yeah. And then C goes to the MSB.
Mm-hmm. So do you want to use SRA for S0 or no?
No, because it could be 0 or 1.
Mm-hmm. That's right. So you want to probably use SR0 for the upper byte, right? So it's keep adding zeros because shifting to the right, so that's actually adding zeros to the front. So that should be applied to S0. And where's C? Where's the LSB? It's in C, okay? However, you do need that LSB to go to what? The lower byte.
Yeah, that's so then we use SRA.
So what is the current C now?
The currency is
The LSB of the first one, right?
yeah.
Okay. However, the SRA is also shifting. See the SRA here is also shifting the LSB to C. So the C will be updated, but does that matter? So I'm asking you to shift everything to the right by 1 bit. What about for 2 bits? For example, after the second instruction, it jumps back to form a loop, right? Just keep doing this.
Yeah.
Does that matter? So let's do the shifting by 1 bit first. Okay, let's complete that one first.
So it'd be SR0, then SRA, and then
Yep, that's right. So SR0 first and SRA second, right?
and then you would set using the
So that's just 1 bit done. It's already done. Just 1 bit. It's done. So what about 2 bits? Let's write another code for another 0.5 points on the right. Can we do two bits?
well, you just have to clear the carry flag, right? And you could just well, actually, wait, no, you keep the carry flag, and then you just loop it, wouldn't you?
Yeah, if it's just a 1 carry bit for everything, right? So after it comes back to S0, it's gonna update it by the new LSB.
Yeah.
Okay, so it doesn't matter. It stores the second one's LSB temporarily.
Yeah.
Mm-hmm. Yeah, the 2 bits you need the counter as well. So yeah, let's do this probably at a later time. So you need the subtraction and check if it's 0, right? For example, set a 2, right? -1. If 0, then done. If it's not 0, go back, right? It's more complicated.
Yeah.
Could be a quiz problem later. Now let's just move forward. Yeah, forget about that. It's too much for now. So the last one. It's converting that C program into a assembly. So come back to this tutorial. It's checking if you look at the paper, okay? Look at the paper. So it's checking if S0 is less than S1 or S1 is larger than S0, then do something. Otherwise, do nothing. So the instruction you can use is compare. So the way you can understand compare is it's actually doing a subtraction. It's subtracting sy from sx. So you can, whenever you see compare, just in your mind, just do a sx minus sy. Okay? So if sx is less than sy, so it's going to borrow. Whenever it borrows, it's set c, the carry bit, will be set to 1. If they're equal, the subtraction turns out to be a 0, then Z flag will be on. Okay? You see here? If Sx is less than Sy, carries on. So it borrows. Keep in mind. Because they are not equal, so Z has to be 0. If they are not equal. If they are equal, Z is 1. C 0. If they are not equal, C is 1. If Sx is less than Sy, C is 1. Z is 0. Right? Okay. So look at this if statement in C. If S0 is less than S1, do this, otherwise do nothing. So you can directly start writing the assembly. It could be a compare S0, comma S1, right? So it's doing a subtraction, it's going to be S0 minus S1.
Yeah.
Okay, then you're checking what?
The carry flag?
C, yeah, check carry. If, for example, let's use NC. Let's use NC. NC means what?
Not carry.
No carry means what?
Carry is 0.
Yeah, carry 0. Carry 0. So they are. No, yeah, we don't know yet, right? It could be another case. Should be. It could be S1 less than S0, right? So which one should we use though? Wait. If it carries, let's use jump C, okay? Jump C. So if we use jump C, jump to something, right? I'll just drop it right here, no, make it easier. Compare S0, comma S1, okay? So it's doing a subtraction, S0 minus S1, S1. If I do a jump, C, if it's a 1 means this is less than this guy. Because if this is less, then do this, right? If it's less, do this. Then jump to where? Jump to do something. So do something is the address here, right? Do what?
Just add S1, comma 1 in hex.
Yeah? Otherwise, do what?
Otherwise, it needs to jump to done, or just some kind of infinite line.
Yeah. Let's do it.
Yeah. Wait, can you do jump NC and have it so that?
Yeah, jump and see. Let's see. Jump and see.
Yeah, that's what it is.
Jump and see. If it's jump and see, so which
You
means
just jump to the.
it could be equal or larger than that, right? So there will be two cases, right?
Well, if they're equal to, then.
Oh yes, which is fine, right? Which is fine. Yeah. So it's jump and see to what? To where?
Like done, or whatever, or the.
Okay.
Loop.
Nothing, right?
And then,
Otherwise,
otherwise, you just add it.
cool.
Yeah.
Great. Any question on this?
That's pretty.
Either way. Five more minutes. Let's look at another one here, multiplication. So you are able to do some multiplication as well. Let's see how that works. It's at the bottom of the page. At the bottom of the page. So this is related to the lab we're going to do next week. So not waste your time. So let's see. This is the core algorithm for multiplication. If I'm using let's give you an example here, multiplication. If I'm doing a 3-bit number times a 3-bit binary number, so for the result, how many bits do I need to reserve for the space for that result, for the product?
9 bits?
So let's see, 3-bit, what's the max number of 3 bits? 7, right? 7. So 7 times 7, 49. So 49 you need, so 64, so which means it will be,
To the 5th?
so how many, what's the maximum number for, let's see, 1, 1, 1. So what is this one? This is 2 to the 6 minus 1, right?
Yeah.
Which is what? 63.
Yes, yeah.
So 63 is larger than 49. So I think 6 bits is a minimum number of bits we should use for 3-bit times 3 bits. So eventually, if you have 3 bits, you probably need 3 plus 3 bits for the product. Okay. It could be applied to other number of bits. We can test it easily, but I think if we have 8-bit number times 8-bit number, you can test it easily. We should have 2 bytes for the product. Okay, so upper byte and lower byte. So we need 2 bytes to hold the product. If you look at the example here, we don't have to finish this, right, but just take a look at it. Let's do this next week, probably. A little bit too much here. All right. See most of you guys this afternoon for the VLSI lab. Otherwise, it's gonna be next week, Tuesday. Right.
So I guess.
Yes.
Actually, so for the